Hello! Hope you are well. Today we are looking at current voltage graphs. I'm hoping that you have already plotted two graphs based off of the table of results that I popped on Google Classroom, and then the aim of this video is to get you to make notes around them. So the first thing is an apology. If we were in school, it won't really surprise you to know that we will be doing a practical with this, and it is a practical that you did at GCSE, but obviously the theory behind it is slightly more complex at A-level. So you are expected to know the practical, and obviously when eventually we are back in school, I will make sure we do the practical. But for the time being, I'm going to explain what you would be doing and the results, etc. So the first thing is, although I'm not going to get you to write down the instructions, these are actually instructions you are expected to not necessarily know, but be able to figure out. So yes, first thing you would do in all of this is that you would connect up the circuit. So the circuit is on the bottom right hand side, and let's just talk through what you can actually see. So you've got a cell which is obviously providing energy, and it is connected to a normal resistor, which you can see on the bottom left, a voltmeter, an ammeter, and then can you see the ammeter has got like a floating wire that seems to go about halfway to a resistor. Now this setup is effectively something you can use to change the amount of voltage and current that is going to the resistor that we're looking at. So we're looking at the resistor on the bottom left, but we want to change the amount of voltage and current that goes through it. And so we use this setup. This floating wire resistor bit is actually another way of drawing a variable resistor, but you may see it referred to in questions. This, yes, has a rheostat. Now that here is your rheostat, and what you'll basically do is you can move this arrow to different points and then affect how much of the resistor you actually haven't forcing it to go through, and depending on whereabouts it is, you will have a different proportion of the voltage that comes from the cell. So if I get rid of all of that, how do I delete this? Delete. There you go. Yeah, so you are expected to know the circuit diagram. So if you could please take a note of that. Then it says record the current and potential difference. Adjust the variable resistor. I'll put in here /rheostat. Record the current potential difference again. Repeat 3 more times. Reverse the connections on the power pack. Repeat steps 2 to 4, 5 times. So what you're doing by reversing your connections is you end up with negative values. So that's what you would do. Then, as you hopefully saw, I'd already given you some results. I gave you 2 sets of results, and although I didn't tell you which one was which, I'm hoping that your graphs turned out one of them like this and the other one like that. So yes. Based off of that, this is us doing that experiment with a resistor. So here was a resistor. If the other set of results, we would replace this with a bulb. So this one is a resistor, and we call it an ohmic resistor. And we say this because it follows Ohm's law. So if you remember from last lesson, Ohm's law says that metallic conductor at constant temperature, the voltage and current will be proportional, basically, and that's what's happening here. So current and voltage are proportional. If you could please add these notes to your graph. Resistance gradient is steady. Actually, it will be the inverse gradient on the graph we've got here, because it's V over I. And behaves the same way regardless of polarity. Now, what I mean by that is, if you have a resistor and then you switch it over, you turn it round, nothing changes. Other components like diodes, for example, work in one polarity. So if you switch them around, they don't work. But this doesn't make any difference. So the next thing I'd like you to add is why this happens. Why does current increase as voltage increase? With a higher voltage, the electrons are given more energy. This means they travel faster. More electrons pass a point per second, i.e. there is a higher current. So let me just play this. Here we go. We've got some electrons going around a circuit. If I add another cell there, so we've now got 3 volts, you can see the electrons go faster. Another cell, 4.5 volts, they go even faster, and so on and so forth. Right, the next thing we're looking at is a current voltage graph for a bulb. Now I'm hoping that you get this like S shape. Now there is obviously a reason for this, and it's all to do with temperature, which again we looked at last time, and its effect on resistance. Current and voltage are not proportional here. Yes, I know they kind of are in the middle, but overall they're not proportional. Resistance, gradient, again it would be the inverse gradient, changes. Behaves the same way regardless of polarity, true, but this time we're saying it's non-ohmic. And by that I mean it's not that linear relationship, they're not directly proportional to each other. And that is because, as we talked about, the temperature changes. So add these to your graph for me, please. And moving on, why is the graph this shape? The filament is heating up. The ions in the filament are vibrating more, so they get in the way of the electrons flowing through. It slows the electrons down and provides, can you change that for me, increased resistance. Lovely, so again, let's just do here, we've got some electrons flowing through. As it heats up, the ions start to vibrate. Here you go, there's a little bit of vibration. Why are they not vibrating? Come on. Oh, sorry, this works better on a computer. I'm just tapping away, but nothing's really happening. There you go, I'm literally just tapping the screen now. Oh, here we go, look, they're starting to vibrate. Oh, it does not work on an iPad. Apologies. Right, so once you've done that and you've added all your notes, please come join me on Zoom and we are going to do some questions on page 146. Thanks everyone.